Hello everyone, this is Vijetha, Associate Professor in the Department of ECE from MLR Institute of Technology. Today I would like to talk on Wien bridge oscillator. These are the topics which I want to cover here. What is an oscillator? What are the conditions for an oscillator? And what is the circuit for Wien bridge oscillator? And how to determine the frequency of oscillation for a Wien bridge oscillator. First, what is an oscillator? An oscillator is a feedback amplifier in which fraction of output is fed back to the input with a feedback circuit. Vi is the input voltage which is given to an amplifier, and the output V0 of an amplifier is again giving as a feedback to an amplifier, where Vd is the actual input voltage for an amplifier which is given as Vi plus Vf. Vi is the input voltage, Vf is the feedback voltage. So, the simplified block diagram for an oscillator is given as amplifier's output is given as a feedback to the input of an amplifier. There are two conditions to satisfy to get a sustained oscillation. They are magnitude of open loop gain and the feedback gain should be equals to 1, and the total phase shift between the open loop gain, that is between AV and the beta, should be equals to either 0 degrees or maybe 360 degrees. What is a Wien bridge oscillator? Wien bridge oscillator is most commonly used audio frequency oscillator due to its inherent simplicity and stability. The Wien bridge oscillator using op-amp is connected to operate in a non-inverting mode which produces a no phase shift at the output. The Wien bridge circuit is connected between the input and output terminal of an op-amp. The Wien bridge consisting of series RC network forming one arm of the bridge circuit and a parallel RC circuit forming a second arm for the circuit. The input resistance RF and the feedback resistance RF forms the third and fourth arms of a bridge circuit shown here. R1 and RF acts as a one arm, and series combination of RC, parallel combination of RC acts as a another arms. It is known that the total phase shift around the circuit must be 0 or 360 degrees for oscillation to occur. It is achieved when bridge is balanced, that is at resonance. Thus, the frequency of oscillation is the resonant frequency of a balanced Wien bridge. Zs is a series combination of R and C, and Zp is represented with R parallel with C. This is a feedback circuit which is connected to a input of an amplifier from the output of an amplifier. How to find out the frequency of oscillation? First, we will be considering the feedback network, which is a series connection of RC and parallel connection of RC. So, let us assume Vf is the feedback voltage, V0 is the output voltage. So, this is the output voltage, that is output voltage of an amplifier given to the input of a feedback, and Vf of S is output voltage of a feedback network. Here Vf of S can be determined by using a voltage divide rule as V0 of S into opposite voltage, that is Zp of S divided by total resistance, which is given as Zp of S plus Zs of S, where Zp of S represents the parallel combination of R and C, and Zs of S represents the series combination of R and S. This equation can be determined by applying a voltage divide rule across the Vf of S, that is at the output of a feedback circuit, where Zp of S can be determined as Zp of S can be given as R parallel with C, that is R is given as 1 by R plus 1 by SA, which you can write as 1 by SC. It is written as 1 plus R SC divided by R, where the Zp of S, this should be a inverse, that is R by 1 plus R SE. So, Zp of S is given as R parallel with the capacitor is R parallel with 1 by SE, which is given as R by RSA plus 1, whereas ZS of S is a series combination of R and C, which is given as R plus 1 by SC, which you can write it as RSC plus 1 by SC. So, ZS of S is series combination of R and C, which is given as RSC plus 1 by SC. Now, we need to find out the gain of this feedback network. The gain here, the feedback network gain is given with beta, which is given as output voltage by the input voltage, where the output voltage is Vf of S and input voltage is V naught of S for the feedback network, where beta is the gain of a feedback network, Vf of S is the output voltage of feedback network, and V naught of S is the input voltage of a feedback network. So, beta can be given as V of S by V naught of S, where from this equation you can write it as Zp of S divided by Zp of S plus Zs of S, where Zp of S can be substituted with R by RCS plus 1 and Zs of S can be substituted with RCS plus 1 by SC. If you can substitute, Zp of S is given with R by RCS plus 1 divided by, and again the Zp of S is given as R by RCS plus 1 plus Zs of S is given as RCS plus 1 by SC. If you can solve this, you can write this equation as R divided by 1 plus RCS divided by this RSC plus 1 plus RCS whole square divided by SC into 1 plus RSC, where this 1 plus RSC and here denominator 1 plus RSC get cancels out, and you can rewrite this expression as RCS, that is RCS or RSC divided by RCS or RSC plus 1 plus RCS whole square. So, now if you can solve this, you can get this as RCS divided by RCS plus A square plus B square, that is 1 square plus R square C square S square plus 2 RSC plus 2 RSC, which can be given as RCS divided by R square C square S square plus 3 RSC plus 1. So, finally, for a feedback network is given as RCS divided by R square C square S square plus 3 RCS plus 1. And as we already discussed that, as we are connecting the input terminal to a non-inverting terminal, the gain or the voltage gain for a non-inverting terminal is given as 1 plus Rf into C. The first condition which has to be satisfied for the oscillator is modulus of AV beta is equals to 1, where A is a open loop gain, beta is a gain of a feedback network. So, we got this 1 plus Rf by R1 as the input has been connected to the non-inverting terminal, and beta which we have derived, which is given as RCS divided by R square C square S square plus 3 RCS plus 1 is equals to 1. If you can segregate this, you can write this as 1 plus Rf divided by R1 into RCS can be given as equals to R square C square S square plus 3 RCS plus 1. If you can substitute S is equals to j omega in the above expression, you can write as 1 plus Rf by R1, this Rc, S is equals to j omega. If you can substitute, you can write as j omega Rc is equals to S square is minus j omega square is j square is minus 1. So, you can write as a minus omega naught square R square C square plus 3 j omega Rc plus 1. If you can equate this expression, if you can separate this expression as a real terms and imaginary terms, if you can equate the real terms on RHS and LHS, you can determine the frequency, and if you can equate the imaginary term, you can determine the gain of a circuit. So, if you can equate the real parts from this circuit, you can write here is 1 minus omega square R square C square is equals to 0. So, the same thing we have represented here. So, if you can equate the real parts from the above expression, you can write this as 1 minus omega square R square C square is equals to 1, as we have 1 plus omega. So, okay. So, this is like this is, after substituting S is equals to j omega, we got this expression. And now if you can equate the real and imaginary terms on both the LHS and RHS side, you can rewrite this expression. If you can equate the real part, you can rewrite this expression as 1 minus omega square r square c square is equals to 0 can be given as omega square r square c square is equals to 1, where omega is equals to 2 pi f. So you can write it as 2 pi, that is 4 pi square f square r square c square is equals to 1, where f square is equals to 1 by r square c square into 4 pi square, and f is given as 1 by 2 pi r c. So you got the frequency of oscillation, the sustained frequency of oscillation at 1 by 2 pi RC, and if you can equate the imaginary parts of LHS and RHS side, you can write this as 1 plus RF by R1 into j omega naught RC, which is equals to 3 j omega RC. If you can solve this expression, you can get this as see this j omega RC and this j omega RC get cancels out. So 1 plus RF by R1 is equals to 3, and you can write RF by R1 is equals to 2. So RF should be equals to 2 times of R1. So in order to get an gain, you need to choose RF is equals to 2 times of R1. So the Wien bridge oscillator circuit can be used in the frequency range of 5 Hz to 1 megahertz, that is at low frequency applications like audio generator. It is not suitable for high frequency applications above 1 megahertz due to the phase shift through amplifier and phase shift of a lead lag circuit jointly causing a resonance to occur at different frequencies other than the specified resonant frequencies. This is why, that is, as it is not giving a exact resonance at exact frequency, this circuit is not suitable for high frequencies. This circuit can be suitable only for a low frequencies because of its resonance problem. So here we have determined what is an oscillator and what are the conditions for an oscillator, that is modulus of A beta should be equals to 1 and the phase shift should be 0 degrees or 360 degrees. And we have determined the circuit. We have discussed about the circuit of Wien bridge oscillator. And we have determined the frequency of oscillation, which is given as 1 by 2 pi RC. And the condition to get a sustained oscillation is RF should be equals to 2 times of R1. And we also determined that, we also discussed that this Wien bridge oscillator is suitable for low frequency, not for high frequency, because of the resonance problem, because it is not resonating at an exact frequency and it is resonating at different frequencies. Thank you.